All right, welcome back to the deep dive. You've handed us a really fascinating stack of sources this time.
Yeah, it's the absolute latest in AI research, really zeroing in on large language models and agents.
Pulled straight from a newsletter covering the top papers just from last week, June 2nd to the 8th, 2025.
That's right.
So our mission for this deep dive is, well, to cut through the jargon, right?
Exactly. To unpack what leading researchers are really finding out about how these complex AI systems, think or learn.
And interact with the world. We're going to boil it down to the key insights for you based on the stuff you shared.
And it's not just looking at each paper one by one, is it?
No, definitely not.
It's more like getting a snapshot of the cutting edge right now. What are the big questions? What are the surprising findings? Where's the field actually going?
And the range here is pretty wide.
Oh, yeah. Everything from fundamental limits on reasoning to new ways to train them and how these AI agents are getting better.
And honestly, some of this stuff is genuinely unexpected. We're going to dig into whether these models really reason like we think they do, or how they might store knowledge in a way that's, well, pretty different from us humans.
Okay, let's dive in. Let's unpack this stack.
So where should we start? There's one here, paper one, that jumps out with the title, The Illusion of Thinking.
Right. A bold title.
It asks a pretty fundamental question. How well do these so-called large reasoning models actually reason, especially when things get tough?
Yeah, and what's cool about this paper is they didn't just use standard benchmarks, the ones models might have already seen.
Good point. Contamination risk.
Exactly. So they used these classic controllable puzzles, things like Tower of Hanoi, checker jumping, river crossing, stuff like that.
Why those specifically?
Because you can precisely control the difficulty. You can scale the complexity up step by step, and you can analyze the model's entire thinking trace, every step it takes, without worrying it just memorize the answer.
Okay, makes sense. So what did they find? The results.
Well, they were pretty striking. They identified what they called 3 complexity regimes.
3 regimes, okay.
Yeah. So at really low complexity, sometimes simpler models, the ones that don't really do chain of thought, they actually do better. They're just more direct.
Interesting.
Then in the middle range, that's where the large reasoning models, the LRMs, they start to shine. They use those longer chains of thought. They can navigate steps, even correct some errors along the way.
Okay, that sounds like what we'd expect.
Right. But then you hit the high complexity regime, and this is the kicker. All the models, didn't matter how big or what reasoning method they used, they just collapse.
Collapse. Like, completely.
Pretty much. Accuracy dropped to near 0. They just couldn't solve the complex versions of these puzzles.
Wow. Okay, but how did they collapse? Was it just too many steps?
That's the really weird part. It was counterintuitive. As the problems got harder, beyond a certain point, the LRMs actually used less reasoning effort.
Less, not more.
Less. Fewer tokens generated in their thought process. It wasn't like they hit a token limit. It seemed more like some internal reasoning process just failed or gave up.
That's bizarre.
It is. And they also saw weird inefficiencies in the reasoning trace itself. Like for simple problems, they'd overthink it, generate these long, unnecessary chains of thought.
Right.
For medium problems, they might make an obvious mistake early on and only catch it way later. And like we said, for the complex ones, the trace just became useless noise.
And it wasn't just about finding the solution path either, was it?
No. That's another crucial point. They even gave the models correct pseudocode, like explicit instructions for solving the Tower of Hanoi recursively.
So they handed them the algorithm.
Exactly.
Yeah.
And the models still failed at similar complexity levels. That suggests it's not just about discovering the logic. It's a struggle to reliably execute logical instructions, even when they're spelled out.
It's a deeper problem.
It really is. And one more thing, performance was really inconsistent across puzzles.
What do you mean?
Like, a model might manage 100 correct steps on Tower of Hanoi, but then fall apart after just 4 steps on a river crossing puzzle, even if that puzzle was technically simpler based on the number of steps.
So it suggests maybe familiarity matters more than pure logical complexity, like patterns it saw in training.
That's what it points towards, yeah. More about recognizing patterns than applying abstract logic consistently.
So if you're listening to this, what jumps out at you there? Is it the idea that they just sort of stop trying when it gets really hard?
Or maybe the fact that they can't even seem to follow direct instructions reliably.
Yeah, for me, it really highlights these fundamental limits in how we're currently getting models to reason.
Totally. It makes you question if just scaling up or adding more thought steps is the answer.
Right. It feels like we need something Different, new approaches maybe.
That seems to be the implication. We need new ways for them to handle complex novel logic.
Okay, well, that leads us nicely into another paper, paper 7, Alpha Known. They seem to be trying a different angle on reasoning.
Exactly. This one's about modulating the reasoning process during inference, controlling the pace of thinking.
Controlling the pace. How?
They use this tunable parameter, alpha, to decide when the model should engage in slow thinking. They actually insert weight tokens into the process.
Like telling it to pause and think.
Kind of, yeah. Pause and deliberate. And then, crucially, they use a specific token, think, to signal, okay, stop the deep thought now, generate the answer efficiently.
Explicitly managing the thinking time.
Right, giving it that temporal control.
And what was the surprising finding here?
It was that slow then fast reasoning worked better.
So think hard up front.
Yeah, front load the effort. That outperformed trying to think fast initially and then slowing down later if needed.
Huh. Interesting. Did it work well?
It did. They saw accuracy boosts up to like plus 6.15%, and sometimes it even used fewer tokens overall, maybe up to 14% less than other methods.
Fewer tokens, but better results.
Sometimes, yeah. And the best way was a linear schedule for those weight tokens, kind of easing off them. But that think token, that was critical, explicitly ending the slow phase boosted performance by up to 20% sometimes.
So clear signals about the cognitive state really matter.
Seems so. It's about managing the process explicitly.
Okay, let's shift gears a bit. We've talked reasoning limits. What about knowledge itself? How do LLMs actually store information, represent meaning? Paper 2, From Tokens to Thoughts, looks into this.
Right. This one asks, is the way LLMs organize semantic knowledge anything like how humans do it?
How did they test that?
They used concepts from information theory, rate distortion theory, information bottleneck, and applied it to the model's token embeddings. Then they compared those structures against classic human psychology benchmarks.
So looking at the relationships between words or concepts in the model's brain.
Essentially, yeah. Do the statistical patterns in the embeddings match human conceptual structures?
Do they?
It's a mixed picture. On one hand, yes, LLMs do form broad conceptual categories that align pretty well with how humans group things.
Okay, so they get the big picture categories right.
Seems like it. Their performance on clustering tasks was much better than random. And interestingly, even smaller encoder models like BERT did as well or sometimes better than bigger decoder models like GPT on this broad categorization.
Huh. Okay. But you said mixed picture.
Yeah, here's the catch. They really struggle with the finer grained stuff, specifically human notions of typicality.
Typicality. Like
Right.
a robin is a more typical bird than a penguin.
Exactly that. When they tested if the similarity between embeddings in the LLM matched human ratings of typicality, the correlation was weak. Inconsistent across models. They just don't seem to capture that graded prototype structure of meaning that's so key for us.
So they might know a penguin is a bird, but not that it's a weird one.
Sort of, yeah. They lack that sense of goodness of example.
Why is that, according to the paper?
They think it relates to the optimization objective. Their unified loss function suggests LLMs might be over-optimizing for compression.
Compression?
Yeah, creating statistically efficient tight clusters with low entropy. Humans, maybe, tolerate more inefficiency in our mental categories to keep richer nuance and flexibility.
So it's a fundamental difference in how meaning is represented. Efficient clusters versus messier, nuanced prototypes.
But that's the idea. It's a divergence in the underlying representation, even if the surface behavior, like categorization, can look similar sometimes.
That actually helps explain that uncanny valley feeling you sometimes get, right?
Definitely.
They sound smart, they categorize things, but then miss subtle nuances or typical examples that seem obvious to us.
Exactly. They might be getting there via a very different internal pathway.
Okay, that connects really well to paper 3, knowledge or reasoning. This one tries to actually pull apart the thinking into, is it getting the facts right, or is the reasoning process itself helpful?
Yeah, they tried to quantify two things. Knowledge index, KI, basically. How factually correct is the stuff in the reasoning chain and information gain, info gain. How useful or clear are the reasoning steps themselves.
Okay, knowledge and informativeness. How did they use that?
They applied it to see how reasoning transfers across domains, specifically looking at medical versus mathematical tasks using
Yeah.
models like Qwen 2.57b, and a distilled version.
And what came out of that comparison, especially regarding training methods?
Well, this showed a real tension. Supervised fine-tuning, SFT, it definitely improved factual knowledge. KI went up like plus 6.2% in medical tasks.
Good. More facts.
But surprisingly, it actually hurt the reasoning clarity. Info gain went down by almost 39% on average. The reasoning became more verbose, maybe redundant, less informative.
Wow. So more facts, but messier thinking.
Kind of, yeah. Contrast that with reinforcement learning, RL. In the medical setting, RL seemed to boost both.
Both knowledge and reasoning clarity.
Yes. It improved reasoning clarity and knowledge correctness, leading to a big jump in KI, like plus 12.4 points on average. It seemed to guide the model towards more factually sound reasoning paths.
Okay, so RL might be better for that balance, at least in medicine. Did the domain matter?
Hugely. Math tasks, as you might expect, relied more heavily on the reasoning steps they had higher info gain.
Right.
Medical tasks depended much more on getting the underlying facts right, higher KI. In fact, for medicine, KI had an almost perfect correlation, 0.998 with accuracy. Info gain mattered much less, 0.698 correlation.
So knowing the right stuff was way more important than explaining it perfectly in medicine.
Pretty much.
Yeah.
And one other quick finding. The base Qwen model did better than a version distilled from DeepSeek R1, specifically in medicine.
Interesting. Why might that be?
It suggests distillation might struggle sometimes with adapting knowledge to a new domain, maybe because the teacher model had different strengths or biases from its own pre-training.
So the takeaway is, training choices are complex. SFT gives facts, but can muddy reasoning. RL might help both in some areas. And the balance between knowledge and reasoning really depends on the subject.
Exactly. It's not a simple trade-off.
All right, so we've seen reasoning limits, knowledge representation differences, training tensions. How are people actually trying to build better models, especially open ones? Paper 4, Open Thoughts, offers a kind of recipe.
Yeah, this is a really practical contribution. They focused on curating supervised fine-tuning data specifically to build better open-source reasoning models.
What do they produce?
They created a big data set, OpenThoughts 3 1.2M, and trained a model on it called OpenThinker 3 7B, and the results are impressive.
How so?
The 7B parameter model hit state-of-the-art performance among Open 7B8B models on tough reasoning benchmarks without using reinforcement learning.
No RL, just SFT.
Just really well-curated SFT data.
Yeah.
It beat models like DeepSeek R1 Distill Qwen 7B by quite a margin on things like AIME25, LiveCode Bench, GPQA Diamond, sometimes like 15, 20 points higher.
Okay, so what was the secret sauce in their data curation? What did they learn?
They were really systematic. They tested each step, sourcing questions, filtering, choosing the teacher model to generate answers, deduplication, sampling strategies.
And what worked?
A few key things. One was generating multiple answers, like 16 for each question. That was better than just having more different questions. Quality exploration per problem beat sheer quantity of problems.
Okay, depth over breadth per question. What else?
The choice of teacher model was fascinating. KeyWQ32B, which wasn't the top performer itself on benchmarks, actually produced better student models than supposedly stronger teachers like DeepSeek R1 or 5.4.
Wait, a weaker teacher made a better student.
It suggests the quality of the reasoning trace the teacher generates is more important for learning than just the teacher's final answer accuracy. How it shows its work matters more.
That's really important insight. Any others?
Yeah, filtering was simpler than expected. Basic filters on response length and using an LLM to estimate difficulty were more predictive of gains than complex verification methods.
Huh. Simple filters win.
And focusing on just the top 1 or 2 question sources per domain worked better than mixing lots of sources. Again, quality and focus seemed key.
So they really provided a blueprint here.
Exactly. And crucially, they released everything, the data, the models, the code. It's a transparent, reproducible benchmark for open reasoning research, which is massive for the community.
That's fantastic. And just briefly tying into that open resource theme, Paper 8, CommonPile v0.1.
Right, another huge contribution, an 8 terabyte openly licensed text dataset for pre-training.
8 terabytes.
Massive. And the models they trained on it, they're comma models, performed comparably to Llama 1 and 2. It just underscores how vital these large, open, high-quality datasets are for pushing the whole field forward.
Absolutely. Okay, let's pivot now to AI agents models designed to actually do things, use tools, interact with environments. Paper 5, Coding Agents with Multimodal Browsing.
Yeah, this one is about building a single unified agent that can handle lots of different tasks.
So not specialized agents.
Exactly. They introduced OpenHands Versa. It integrates code execution, web browsing, including images, multimodal, file access, search, all into one system. The idea is to avoid needing lots of specialists or complex multi-agent setups.
And did this unified approach work?
Surprisingly well, actually. Despite being a single system, OpenHands Versa outperformed specialized agents on 3 different benchmarks.
Which ones?
SWE Bench Multimodal, it was over 9% better. GAIA, about 1.3% better. And the Agent Company benchmark, over 9% better again.
Wow. So better than the specialists. And multi-agent systems.
Yeah, it also matched or beat multi-agent systems, which often struggled when they faced problems outside their main expertise.
Why did the unified approach work so well here?
It seems to be about adaptability. The agent could intelligently pick the right tool, browsing, coding, searching based on the specific task. Their previous version, OpenHands, often failed because it misused tools or just didn't have the right ones integrated.
So having a general adaptable toolkit in one agent was key.
Exactly. That seamless integration and adaptability seemed powerful. They even hit state-of-the-art on the GIA validation set using standard backbones like Claude 3.7 or Sonnet 4, minimal new architecture, just effective tool integration.
Very cool. Okay, another agent paper, paper 6, self-challenging language model agents. This sounds intriguing, improving without human feedback.
Yeah, this is a really novel idea, the self-challenging agent, or SCA. The core concept is the model trains entirely on tasks that it generates itself.
It teaches itself. How does that work?
It uses a dual agent setup. One agent acts as the challenger. It explores, creates new tasks, and provides a way to verify solutions. The other is the executor, which learns by trying to solve those tasks.
Like setting its own homework and grading it.
Kind of, yeah. And they created a new task format called Code as Task, or CAT.
Code as task. Tell me more about that.
So these aren't just text instructions. A CAT includes the instruction, but also a Python function that automatically verifies if a solution is correct, a working example solution, and even examples of common failure cases.
So the verification is built in and automated.
Exactly. This automatic code check filters out bad or ambiguous tasks, ensuring the synthetic data is actually high quality. It mimics human annotation, but scales massively without needing humans in the loop.
That sounds powerful. Did it improve performance?
Significantly. Just learning from its own CAT tasks, the SCA method doubled the performance of a base Llama 3.18b model on the benchmark they used from 12% success to 23.5%.
Doubled it. Wow.
And when used for distillation learning from a bigger 70B teacher model using SCA, it pushed the 8B model's success rate up to 32.2%, beating previous methods. Human evaluators also confirmed the CAT tasks were better quality, less prone to errors than other synthetic data generation techniques.
Any other key takeaways from that one?
Yeah, an interesting scaling insight. Creating more diverse tasks led to better generalization than just generating more attempts or solutions for the same tasks.
So breadth of synthetic experience matters more than depth on a few tasks.
Seems so for building robust agents.
Okay, let's start to wrap up with a couple of papers on evaluation and fundamentals. Paper 9 introduces Reward Bench 2. What's that about?
This is about evaluating reward models, the models that are crucial for alignment techniques like RLHF, reinforcement learning from human feedback.
Right, the ones that judge if an AI's output is good or preferred.
Exactly. Reward Bench 2 is designed to be more challenging than its predecessor, using trickier human prompts. It's also engineered so the reward model's score correlates better with how well the actual language model performs downstream.
Is it revealing anything new?
It is. Existing reward models are scoring about 20 points lower on Reward Bench 2 compared to the first version. It shows there are gaps and that we need better evaluation tools like this to really drive progress in making AI systems helpful and harmless.
Better benchmarks push the field forward. Makes sense.
Definitely.
And finally, a really fundamental question tackled in Paper 10, memorization in LLMs. How much did they just regurgitate versus actually generalize?
Yeah, this is a deep one. This study offers a way to actually try and quantify the difference.
Quantify memorization. How?
They developed methods to estimate it. For GPT models, their estimate is around 3.6 bits of memorization capacity per parameter.
3.6 bits per parameter.
Yeah.
Okay. What else did they find?
By training lots of models, they observed a really interesting dynamic. It seems like memorization capacity gets filled up, it saturates, before the model really starts to generalize effectively, that phenomenon sometimes called grokking.
So memorize first, generalize later.
That appears to be the sequence, yeah. They even derive new scaling laws that connect this memorization capacity to the amount of training data and how easy it is to perform membership inference attacks, figuring out if a specific piece of data was in the training set.
So this gives us a more concrete handle on the learning process inside these huge models.
Exactly. It suggests it's not just one smooth process. There's a distinct phase of soaking up specifics before the broader pattern generalization really kicks in. It helps us understand the underlying dynamics better.
Wow. Okay, that was quite a journey through, what, 10 papers from just one week?
Yeah, a rapid tour.
We went from seeing these surprising, maybe concerning, limits on complex reasoning to how models might represent meaning in a fundamentally different way than we do.
Right, that compression versus nuance idea.
Then we saw practical recipes for building better open models, new ways to make agents teach themselves.
With self-challenging agents, yeah.
And finally, getting a glimpse into the basic mechanics of memorization versus generalization.
It really is a snapshot of the cutting edge. You've just gotten this curated look at some genuinely interesting, sometimes counterintuitive findings.
Not just headlines, but the details that matter.
Exactly. The specific results that challenge assumptions and show where the field is hitting walls, but also where it's finding clever new paths forward.
Well, thanks so much for bringing these sources to us. This was fascinating to dig into.
Absolutely. And maybe here's a final thought for you to chew on, tying some of this together. Think about paper 1 showing those reasoning limits on hard problems. Combine that with paper 2 suggesting their internal representation of meaning is different, more statistical, less prototype-based. And then add paper 10's insight about memorization saturation happening before generalization.
Okay. Reasoning limits, different representation, memorize then generalize.
Right. What does all that taken together really tell us about the kind of intelligence we're building here? Are we creating systems that are incredibly skilled at mimicking human-like output, performing complex pattern matching, maybe even acing tests?
But through internal processes that are just fundamentally alien to human cognition.
That's the question. And if they are fundamentally different inside, what are the implications as we rely on them more and more? Something for you to ponder as you interact with AI out there in the world.
Definitely food for thought.
Yeah.
A lot to think about there. All right, that's all the time we have for this deep dive. Thanks so much for joining us.